Okay, welcome back. So today the topic is a slightly different compared to our previous lecture. So today we are going to demonstrate the heat transfer. So maybe I think the Professor Kim Shin will touch you guys last year about the heat and mass transportation. So in the heat and mass and transportation, maybe they use some numerical method, which are most famous method, finite difference method. So today I'm going to introduce you how to make or apply the FEM method for the heat transfer or mass transportations. So today lecture containing the chapter 13 maybe, so that please review after the lecture. So there are many example problems, so I'm not sure that I'm going to dealing with the heat transfer for our final exam, but I think that heat transfers is the most important topic. It is because the solid structure also can be affected by the heat, due to the heat, so that solid structure will expand it, so that so solid structure also experience some the heat summer stresses, so that heat transfer is also important in the solid mechanics. Today running object is we are going to drive some basic difference equation for the heat conduction in the one-dimensional cases, so that maybe in this chapter, end of the chapter, so maybe we are going to also, I'm going to introduce the two-dimensional cases problem either. So however, the one-dimensional heat transfer model is enough. So in the, maybe we should know that to understanding the or handle the heat transfer, we should know that concepts of the conduction or convection and radiation. I'm not sure where is the radiation. So, but anyway, so that those kind of heat transfer mechanism can be inserted into our basic difference equations. So these three are main key concepts about our boundary condition or governing equation, depending on the form of the mathematic equation. So so let's go to the more deeply. So this problem, non-structural problem, this is our first non-structural problem for our FEM simulation. So in this chapter we are considering the heat transfer problem, so many solid structure will experience or expose the different heat environment, so that due to the large heat difference, so that there are some heat flux, so that there are many different types of the heat convection or conduction, radiation. Those kind of heat flux can be used as a convection or radiation, or conduction is a heat transfer inside in the solid structure. So maybe depending on the our system, we can obtain the temperature distribution inside solid structure. This is a high temperature and this part is a low temperature, so that there are some temperature gradient, so that due to the this part solid structure will experience a large volume changings, this is a small volume changing, so that due to the volume difference, misfit strain can be generated inside in the solid structure, so that solid structure experience a large stress resistance, so that if we have enough large temperature gradient, that this volume difference enhanced, that means the stress accumulated inside in the solid structure, so the mechanical will experience some mechanical failures. So those kind of temperature problem also very important in the if you want to consider the solid component. So anyway, so in here we are going to cover something of the equation. So let's go to the more details. So let's drive some basics equation here for the heat transfer. So yeah, 1D without convection. Yeah, so due to the convection containing some temperature variable on the inside, so that make us more harder. So at first time we skip the convection equation. So let's think about this representative volume element. In this volume, so we should check the energy convergence, so that yeah, energy in and energy out must be equal, and then energy generated inside in here, so that must be equal to the internal energy increment, so that we can say that the energy balance equation looks like this. Yeah, inserted energy, input energy is equal to the flux with the cross-section area and enough time. This is a energy inserted into this volume side. And also, if we have some uniform energy generation inside volume and with the same time, the Q is energy densities maybe. So that this must be equal to the internal energy changings and then heat flux outside. So this is energy balance equations. So Q, normally we also say that internal heat source. Oh, sorry, yeah, there are here's terms. So yeah, this heat flux follow the Fourier's first law, so that this equation has some physical meaning. Heat flux is proportional to the temperature gradient. Without temperature difference, there are no heat exchanges, no heat flux. However, they have a temperature difference. Yeah, heat tend to the flow to from high temperature to low temperature. However, this tendency is also affected by the different length scale L and L prime. So the heat tendency can be affected by the length scale. So that means that yeah, heat flux is affected by temperature gradient. So that depending on the material, so that this heat can sometimes yeah, let's think about an wood and steel. Yeah, let's compare the wood and steel. Yeah, wood, yeah, in the steel, yeah. So we in the cold winter days, so when you touch the steel, you feel the very cold. Yeah, it is because that yeah, steel transferred a lot of heat flux from your hand to the steel ion. However, yes, when you touch the wood, yeah, you feel the very warm, actually warm compared to the steel ion. It is because that yeah, wood cannot transfer enough heat from your hands to wood. It is because they have a different heat conductivity. So that in to match this relationship, we need some coefficient. We call it the thermal conductivity coefficient. So we can say that heat flux is just proportional to the temperature gradient opposite direction. So this is a definition of the heat conduction problem. So if you cannot agree with this assumption, you can add it or modify this equation. So however, in the heat transfer, especially heat conduction phenomena, they follow these simple linear relationships. So, and also similarly, the outer part, heat conduction, also can proportional to the thermal conductivity and temperature gradient at out point. So that using the Taylor expansion series method, we can modify this equation to this temperature gradient to the at position x. So this is a first order Taylor expansion, and this is a second order Taylor expansion series. So that, and then we can also define the internal energy. So the internal energy can be defined by the specific heat and mass and changing temperature. So that, so internal energy also affected by temperature changing, and then heat capacity and total masses. A and dx equal to v, and rho is a density, so that this become the mass. So that so we should match the energy balance equation. Maybe the qx equal to the energy generation in the previous slide. Where is the qa dx dt is equal to the internal energy c rho a dx, the temperature gradient, and qx dt. But so in here, they have a same two terms in here. This part, so that you can cancel out each other. So that the remaining things is when you move to the right hand side, and then qa blah 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 and c rho a dt. So that we can obtain those kind of relationship. So, and then we can remove we can neglect to a dx dt, but we can cancel out dt. So finally, we obtain those kind of one-dimensional equation. This is a difference flux, and then this is a heat generation, and this is a changing of the internal energies. So so this is a basic heat energy conservation equation without convection problem. So some temperature Laplacian is and then heat generation is equal to the internal energy changings. So in the steady state problem, so that there are no changing with respect to the temperature, we can negligibly look this term so that they become equal to 0. And then for more simplified, so and we can sometimes negligible, we don't have any heat generation inside the material, so that we can also neglect Q. But anyway, in this time, so we can keep going. So final equation sometime looks like this. It's a very simple partial difference equation. I think that you guys can already know that how to solve this problem using Galerkin residual method. I think that I will give you some those kind of very general cases, so that I think you guys can easily solve this equation. And then, so to solve this Laplace equation, we need two boundary conditions. First is the natural boundary condition. The other is the natural boundary condition. Both are the boundary condition and specific domain. So it is because that we must take integration 2 times. That we need integration coefficient 2. So we need 2 boundary condition. Similarly, 2-dimensional cases, we guys can obtain those kind of equation in the steady state problem, so that this equation also can be easily solved by our FEM method, although I do not introduce yet. So, and then one boundary condition is a specific temperature boundary condition. That means that I'm going to fix this part temperature TB, and also the other is this is a flux equation, so that we can go apply some specific heat flux. And that term is looks like this, and this become some specific constant fluxes. So this is just second types of the boundary condition. So in the two-dimensional spaces. So, however, due to the convection, this heat transfer equation slightly must be modified. For the conducting solid, in the contact with the fluid, or there will be a heat transfer taking place between the fluid and solid surfaces. So if they have some temperature difference, so that means that in the some media in the solid and liquid phases, they have a temperature solid and liquid, they have a temperature difference. Due to this temperature difference, we some fluxes will be flowed from side to the other side, so that we are going to say that this is a convection. So first, there are two types of convection. First, the convection is when fluid is motion through the external pumping action, so that we can, when you apply some external forces to fluid, this fluid part, so that at that time, this liquid phase, maybe a few times later, so few months later, they become obtain the specific temperature. However, due to the movement of the fluid, so the temperature will be changed externally, so that we going to say the first convection. However, natural or pre-convection also can be say that, so that without any treatment, so this liquid or gaseous phases environment also has a different temperature, so that due to the temperature difference between the solid phases and liquid phases or gas phases, so there are some convection from to the other side depending on the temperature, so that we can at the time. So, and then there are no external movement in the gases or liquid phases, we are going to say the natural convection. So however, if you natural convection is we only consider the temperature gradient. However, if you want to consider the first convection, at that time you should calculate the movement of the fluid. That means that you should consider the fluid dynamics. So that's the problem. Heat transfer and fluid dynamics. However, this temperature gradient is solid. So three physics are coupled to each other. So generally, all physical problem. So I think that you guys already learned about the solid and heat thermodynamics and fluid dynamics and just dynamics separately. However, I do not think that those four major topics are independent of each other. They are coupled to each other, or physical phenomena, so that you should know that. And then these days, my major is battery engineering, so that and here and there are some electrochemical reaction and then current flow. That means that all systems are coupled to each other. So I think that you should think or understand the physical phenomena with considering major and another major either. So these days, some fusion technology, it's also very old or boring term of the fusion technology. However, I strongly recommend to you guys to understanding other physical phenomena. And then when you think about some real physics devices or system, that you can imagine that how can we solve it, and then what physics problem are coupled to each other when you're designing something or solve some problem. So that in here, so anyway, so however in this time we are going to neglect the process convection, so we are going to handle the only natural convection system. So let's think about this representative volume element. So yeah, let's consider the energy balance equation once again. This is a heat flux, input heat flux. This is where is the output heat flux, and then heat generation inside the volume, and the internal energy changings inside volume, and then yeah, this is a heat convection. This heat convection has those kind of mathematical relationship. Heat convection coefficient and then temperature difference between the external environment and the solid temperature. What is the problem? We know that environment temperature. However, solid temperature are varying during the until they become saturated. Temperature will saturated, so that amount of the heat flux, heat convection flux are vary. Convection varies with respect to the time. So this is I want to say that this is an unknown coefficient. That means that although we are going to apply this convection as a boundary condition, however, we are not sure, we don't know yet about the boundary condition. That's the problem. When you apply some boundary condition, we know that already the exact values or condition of the boundary condition. However, this convection problem, we are not sure yet about the quantity or value of the convection boundary condition. So that means, so this temperature part must be go to the carbon equation. It makes me confusing first time. However, I think that you guys already handled this problem in the last year, so I don't think that that's the big problem anyway. Let's think about dividing by this volume and time term, so that we obtain the one-dimensional heat conduction with the convection problem. So that this is a conduction of the heat in the one-dimensional solid structure. This is a heat generation, internal energy changings, and then this part is a convection. So we are going to negligible time dependency. So we are only handle the stationary cases, steady condition, and then we are going to also negligible heat generation inside in the solid particle. So sorry. So so anyway, so and then let's think about another types of boundary condition once. So that actually this convection is a heat flux. In the conduction problem, we consider the conduction. Convection. How can I say conduction. This is also heat flux conduction. That this must be same at the specific boundary condition. If we have a solid structure in this part, this is a convection. This is a conduction. That must be equal to each other. We are going to say that this is a temperature boundary condition. So that although we say that this equation defined by specific domain, in the mathematically on the specific volume domain. However, this convection only defined on the specific surfaces. So that this is a slightly wrong expression of our governing equation. So only can be determined looks like this. So anyway, so yeah, please be sure the unit of our system. So let's go to trying to the heat conduction problem using FEM method. Yeah, FEM method is used for predicting the temperature distribution on the thermal stresses in the body. So that first to determine the thermal stresses, so we should know the temperature distribution first. So that means that we should solve the heat conduction problem inside solid media using FEM method. So let's think about and similarly, displacement function can be determined by looks like this. Similarly, in here we are going to say that unknown variable is temperature. So the temperature is also determined by similarly A1 and A2 and what? Temperature specific a specific coordination system. However, we say that this N1 is a coordination function of the x, and then at each nodal point we are going to say that displacement can be replaced by the temperature. So that this is our assumption of the shape function or interpolation function. We are going to take the same interpolation function similarly in the truss and cases, so that temperature exact on the nodal point we are going to obtain the exact temperature values, so that inside the element we are going to interpolate using the linear interpolation shape functions. So temperature gradient, so we are going to use a matrix G. So that, however, let's think about in the previous slide, temperature is they have those kind of T1 and T2 relationship. This shape function is a function of the x, so that dx dt can be n1 n2. T1 T2 is not a function of the x, so that only shape function must be derived by with respect to the x. So that this is a B matrix's part. That B is obtained by substituting the temperature function into the temperature gradient. Looks like this. And then we already know that N1 is 1 over L minus x, and 2 the 1 over x. So that the derivative with respect to the x is 1 minus 1 over L, and the second element is 1 over L. So that heat flux temperature gradient relationship and looks like this. Conduction is we say that thermal coefficient, and then temperature gradient. This is a G, this D is a thermal conduction problem. So in the one-dimensional cases, matrix property is equal to scalar, but in the two-dimensional case they become a 2 by 2, and three-dimensional cases they can become 3 by 3 matrices. So here, so to derive our governing equation, we are going to use potential energy minimum approach method. To using this energy method, we should know that total heat potential energy first. So I'm going to skip the detail about how to determine the heat energy, but if you are interested in the thermodynamics and heat transfer, you guys can easily determine if not, you guys can also use a Galerkin residual method. It is because that we already have second order partial difference equations, so that without any changing of the equation, you guys can easily derive the heat conduction equation for the FEM. However, in our textbook, they derived using the total potential energy minimum approach method. The energy, total energy can be determined by the internal energy at the heat sources energies, and then heat fluxes energy, and convection energy. So that similarly, yeah, internal energy can be expressed the yeah, energy gradient maybe. So 1/2 energy gradient, sorry, not second. Using those kind of way, we can define the heat energy looks like this, and then this part is heat energy source, and then T is a temperature. So then when you multiplying the total volume, you guys can obtain the heat energies. Yeah, maybe flux and temperature can become the energy. Sorry. Yeah, similarly, so that you guys flux and temperature multiplication can become energy. So that yeah, flux's energy is a second order multiplication. So actually I'm slightly confusing how to determine this energy term. So anyway, however, these fluxes are only defined specific surfaces that become a boundary condition. Yeah, on these two terms are defined on inside the volume. So that these two terms is governing equations of our problem. So after the reorganizing, the equation can be expressed looks like this, and that this is a total energy. So that we hope that this energy become minimum. So that yeah, inside in here, what is the unknown variable? So that what, yeah, T1 and T2s are unknown variables. So that actually T. Yeah, so that yeah, to minimize the temperature, the only way to handle is controlling temperature variable. So that each temperature element, the energy must become the minimized. That means that a partial difference equation of the total energy by the temperature variable become equal to 0. So that in here, so that we have two square of the t, maybe g have a t, and in here t, so that we remain only single one, and square cancel out each other, so that they are cancels, it cancels and cancels each other on only one thing. So that finally equation can be expressed looks like this. So and then, but important thing, yeah, this volume determine, yeah, very important in here. And then yeah, second, I think that this is a yeah, first, second, third, yeah, both, sorry, but so anyway, so this part is sorry, yeah, this can become FQ and FQ, and this is FH. So that yeah, this is also FHs. However, yeah, we distinguish the two terms. It is because that yeah, convection, one component has some unknown variable T, yeah, here. So that we cannot say that this is a boundary condition, although the form is this part can be defined only the specific boundary surfaces. However, this two terms is governing our governing equation, and then the other is just the forces terms. The forces matrices can be expressed and look like this. And then finally, our local stiffness matrices looks like this. Yeah, in the compared to in the previous one and then solid mechanics part, so that yeah, B, dB is same form. However, when you if you want to consider some conduction problem, we should adding this term at only specific surfaces, not all volume area. So yeah, so you guys can easily obtain that this is a K, and then B transpose B matrices, they return those kind of 1, -1, -1, and 1 matrices, A over L square, but the integration region, the A is cross-section area, and then after the L, so the L square become the L, so that this is a local stability matrix without the convections. However, yeah, we need some more part. Yeah, in here, what is the L? Yeah, 1 over L minus X and maybe X, so that multiplication these two transpose term, yeah, you guys can obtain the second order polynomial equation after the integrating on the specific surfaces. We can obtain this part. 잠깐 한글말로 해드리면요, 컨덕션만 있을 때는 뭐 저희가 이미 알고 있는 뭐 빔 트러스 요소랑 너무 똑같이 모양이 나옵니다. 하지만 히트 트랜스퍼를 고려하시게 되면 이 정도 항이 추가된다는 건데, 이쪽 적분을 수행을 해보시면 좋긴 하는데 저희가 적분 구간을 정확하게 모르죠. 그렇기 때문에 이 값이 나온다 보장을 못 하는데, 이거 어디서만 정의되죠? 지금 특별한 면에서 이렇게 볼륨이 있으면은 이쪽 면에서만 정의되기 때문에, 저희가 만약 요소를 많이 자르게 되면은 이 요소 계산하실 땐 여기 항이 없죠. 네. 여기에 관련된 요소가 있을 때만 이 항이 나타나는 겁니다. 헷갈리시면 안 되겠습니다. So, and then similarly, the heat source and convection and other heat flux boundary condition can be expressed and looks like this. And then this process only define the specific boundary conditions. So those kind of way, yeah, after the assembling global stiffness equation and then also global forces vector, and finally we obtain the global stiffness equation for the heat transfer problem. So that after the taking inversion, yeah, or you guys can easily obtain the temperature distribution. Yeah, this is a same form, so that please refer the example of our reference problem. That please solve this problem at least one cases. That, however, yeah, actually I don't like convection problem. However, all heat transfer problem related to the convection, so that, yeah, you please be sure that the convection problem either. But however, if you do not want to the convection problem, so that please you guys can fix the specific temperature, yeah, cases, and at that time we don't need to worry about the convection problem. However, yeah, it does not, it can use a very limited cases. That so that I think that Professor Dong-Hok Kim and Professor Kim Shin also introduced the convection problem in your system. So that, yeah, FEM method is only numerical method to solve the problem, so that we cannot handle the convection problem more easily. So anyway, yeah, let's go to the check more two-dimensional cases. Yeah, similarly, yeah, let's think about the three node triangle element. Yeah, so the temperature, yeah, can be determined with the three shape function and three coordination temperature, nodal temperatures. So that, yeah, shape function, yeah, do you remember the exact values of the alpha, beta, gammas 1? So yeah, I think that at least one time you should memorize the exact values, so that you guys can easily derive these values. But I don't think that we don't have enough time to starting the derivation of this coefficient. So anyway, yeah, so that temperature gradient matrices also can be expressed and looks like this. And then, but temperature, yeah, how can you derive it? Yeah, we have three shape function. Yeah, exactly ni ti. So ti. So we have a three component summation, but yeah, each shape functions are derived by the x, and then second terms also derived by the y. So that, yeah, temperature gradient expressed and looks like this. and then this we can say that B matrices of the conduction problem. Yeah, this is a slightly different. Yeah, do you remember the B matrices in the strain component? Yeah, so it was slightly different compared to your system. So yeah, please be sure that sometimes although we use the same types or same form of the shape function or interpolation function, however, their derivative forms shows a slightly differences. So anyway, yeah. So we say that this is a B matrices of the heat conduction problem. The result looks like this. This is some coefficient only. So finally, our final goal is BDB equations for the only conduction problem. So you guys can easily say that the B is 1/2a, so that we have a 1/2a, 4a square, and then this alpha gamma, and then we have a heat second two-dimensional heat conduction coefficient, so that this is a local stiffness matrices of the only conduction part. So that you should adding the convection part separately. So however, integration of this equation is very important. Fortunately, inside integration are constant scalar values. So that means that we don't need to integrate. We obtain the volume. T is a thickness maybe, and then A is a cross-section area of the geometry. So that this is a elastic stiffness matrix of the conduction part, and the convection part can be said that looks like this. So unfortunately, this part, let's think about N1 is 1/Lx, and then I is the same thing. So square means that they return the those kind of second order polynomial equation inside in here. In this time, you guys can integrate this equation. Only h and thickness direction. You guys can return the thickness direction only. However, so I'm not sure that the remaining x, how can you integrate this part? You can, sometimes you can easily integrate it. However, more convenient way, you should apply the Gaussian quadrature integration. That's why I do not like convection problem. To handle the convection problem, we need some Gaussian quadratures inside in the carbon equation. There are no way to escape this problem. So anyway, a common practical heat transfer problem is that the source of the heat generation present within the very small volume of the areas of some large media. They may be idealized and line point sources, so that means that all point sources we can handle the specific point or specific line element. So however, depending on the system, but I'm not sure that in this time, specific point, if we have a special heat source at that time, although we can distribute this heat source to the each node equivalently, but the simplest way is weight average the distribution, but that means that 1/q and q over 3 is the easiest way. However, also using the mathematical equation, actually distributed forces, you guys can share the exact heat sources properly, but it's not out of scope today. So in the three-dimensional cases, you guys can also derive this equation looks like this. And then similarly, but we don't learn yet about the three-dimensional FEM method. I'm going to skip detail. So that using the computer simulation, we are going to handle the three-dimensional cases also. So that if you have some those kind of semiconductor device chip or IS chip or heat cooling microchips, so that in this system, we guys using the FEM method after the discretizing the solid structure, we can apply our governing equation and boundary condition properly, so that after the clicking, computing, you guys can obtain the temperature distribution. Although we only handle the stationary cases, static cases, however, those kind of transfer, time derivative, time dependent, or actually dynamics, we can obtain the time evolution of the temperature distribution. So maybe the your final term project, I hope that you guys select the good cases which help you your career. So 먼저 열 전달 문제에 대해서 여기까지 조금 얘기를 해봤습니다. 저희가 뭐 자세하게 문제를 풀어드리진 않았는데, 제가 아마 다다음 시간 정도에 이제 여러분들 숙제 이제 솔루션을 업로드 해드리면서 숙제를 한번 좀 풀어보는 시간을 갖도록 하겠습니다. 그때도 한번 열 전달 문제를 한번 좀 볼 텐데요. 먼저 책의 교재를 보시면은 hit conduction, 오늘 이제 conduction이 있는 경우랑 convection이 있는 경우랑 식이 조금 달라진다라고 그냥 살짝만 보여드렸는데요. 컨덕션 정도만 들어가 있는 경우는 아마 여러분들이 쉽게 손으로 푸실 수 있으실 것 같고요. 그 결과는 저희 고체역학에서 배웠던 트러스 문제랑 거의 유사하게 나왔던 걸 확인할 수가 있습니다. 그래서 그렇게 한번 1D 케이스에 대해서 뭐 끝에 온도는 0도, 저쪽 끝에 온도 100도 하면 그 사이의 온도 분포에 대해서 너무 직관적으로 우리가 알고 있긴 한데, 그런 경우에 한번 물어 문제 예제도 있거든요. 그래서 한번 풀어봐 주셨으면 좋겠고요. 저랑 한번 더 볼 거고, 또 이제 아마 이번 주 콤솔 시간에는 이런 열 전달 문제를 갖다가 풀어주는 거에 대해서 한번 진행을 한번 해보도록 하겠습니다. This is the end of today's lecture. If you have any question, please send the email anyone anytime when you want. 다음 시간에 뵙겠습니다.